All right. We know that. See if I can get a picture of myself. I'm not talking to a blank piece of paper, and that we know that quantum mechanics is truly disturbing to us and is an experimental nightmare. We know that it keeps showing over and over again that this, in fact, is the way the universe works, and that we just need to get over ourselves and our view of the universe. Relativity is different. Relativity, actually, some of you are going to think, well, that's not that unreasonable. I can deal with that. Some of you are going to think that I still don't like it. But at least it's a much more reasonable way to look at the universe. Also, relativity is more directly testable. You're not talking about random particles you can't see, trying to figure out where they are, waiting for them to appear out of thin air. This is a little different. We can actually make pretty good measurements, pretty good mathematical measurements of these things. So therefore, I'm going to now head into relativity. Now, remember that there were some experiments we talked about before. The problem with these experiments was that one of the experiments in particular was disturbing to us, who had to involve X-ray crystallography, because we had particles that were snapping back after being hit by an X-ray. They were snapping back forward with a pretty good velocity and then sending out light. And when they'd send out that light, it would be traveling the speed of light, which makes no sense because it's being shot from something that is already moving. It would be equivalent to you're standing on a bus, you throw a ball forward, the bus is going 10 meters per second, you throw the ball at 20 meters per second, and the ball still goes 20 meters per second. Well, that can't be, right? Because if you're standing on a bus and you're standing on top, you throw a 20, that has to be going 30, but it's only going 20. Something's wrong with the universe. And so the chemists, being chemists, just said, it works, don't ask questions. The physicists were like, we're almost done with physics here. I want to finish this experiment. I want to show you how it could possibly be done. Went decades. Nobody's come with an answer for why this is. It doesn't make sense. Along comes Albert Einstein. Albert Einstein is a genius. Why is he a genius? Because he says whatever it says. He's basically of the opinion, well, for photons, well, if light has to be a wave, it has to be a particle. Can it be both? Hey, guys, brilliant. He does the same thing with this. He says, well, look at this picture. Okay, fine. It can't go, maybe light goes the speed of light. Ta-da! Genius. But Einstein, that doesn't make sense. Doesn't matter. It's what's happening, so why sweat the details? Well, all right. Then he goes a little farther. Says, if that's true, there's some other things we know are true. What are some other things that are true? Other things that are true is this. We know, well, first of all, this is the third postulate of special relativity, that light goes the speed of light. Speed of light. The first postulate of special relativity is all motion is relative. I'm really botching this up. Relative. What that simply means is that if 20 meters per second, you have a car going this way, the people in this car, if they're going at constant speed, can say, hey, car approaching me at 40 meters per second. And that experiment would look exactly the same to them as if they were at rest. The trees would be moving 20, and the car would be moving 40 at, right? And then, you could say, well, it would notice you're going 1,000 meters per second 500 meters per second this way because the Earth spins. So really, you're going 520. This one's really going 480. And again, same thing. When the collision happens between these two cars, the relative speed is 40. So all motion is relative. So I have a right, as long as I'm traveling at constant speed, to have my reference frame. well, why I constantly, why can't I be accelerating? Well, the answer to the question is try playing racquetball in the back of a truck. You're in the back of a truck, truck's going down the constant speed. Everything's good. The ball's bouncing off the wall. You're hitting the ball. Boom, boom. It's the same whether the truck's moving or going at a constant 20 meters per second. You can't tell the difference. But if the car, the truck, starts accelerating or turns, all of a sudden the person inside is going to notice there's something wrong with the ball. Is going to start bouncing in strange ways. And so accelerating reference frames are exempted from this. This is a really important exemption. The bottom line is, as long as I'm traveling at constant speed, I have a right to my reference frame. My reference frame says that I can describe every other object and how it's moving relative to me being stationary or basically being the boss. That's the first one, motion's relative. The second one is this. Einstein goes on to say this, no place is better. Now this is interesting. It says that there is no place where the actual speed is zero. Where would that be if there was one? There's none. So at the end of the line, this must be true. The first thing must be true, which is we know this is true. All motion is relative. You have a right to look at your own reference frame. Your experiment would look the same whether you choose your reference frame, another reference frame, or any other reference frame. We used that idea before. No place. A new idea because we're used to saying, well, you know, relative to the Earth. The Earth. How fast is a car going? Well, relative to the Earth. We all understand that. Well, why relative to the Earth? Why not relative to the weed in the backyard, or why not relative to the stream in your why just has to be the Earth? The answer is it doesn't have to be the Earth, right? Nobody else would pick the Earth except for human beings. Number 3 is light goes the speed of light. This is profound because these other two directly fight it. Right? How is that so? Well, let's take a look at this idea. If this is true, delete. If this is true, let's go back to our bus. Let's go back to our bus. Driving down the road. We've got a guy throwing a ball. Is it at 20 meters per second? We got a person standing on the side watching it there. 10 meters per second bus. So what do we get? We get the guy on the top says, hey, that ball is only going 20 meters per second. Real ball. That's just what classical mechanics said all along. The people on the side of the road would say, hey, ding, second. But they would agree that that's simply because one's on the bus and one is not on the bus. So what's the problem? Well, let's say the bus instead is going 10 meters per second and shoots light out the front. Been watching the light? So the person sitting in the bus would say, oh, well, light is going up. Light goes the speed of light, and no place is better, so light goes the speed of light. And the person on the side of the road? Well, light goes the speed of light. Now, here's the problem from a classical mechanics point of view. Wouldn't I have to argue that this guy is wrong? But he can't be wrong. All motion's relative. He's traveling at constant speed, doesn't lose the right to his own reference frame. No place is better. He's got to be right. This guy's got it wrong. And speed of light, no matter where you are. So therefore, all of them have to be right. Now, there's a couple of suppositions that come with this. One of these is you can't go fast at the speed of light. Why? Because light goes at the speed of light. If I shoot light and I'm going fast at the speed of light, light would have to have an anti-speed relative to somebody else, so that wouldn't work. So therefore, you can't go fast at the speed of light. If you get near the speed of light, light would look like to this guy, it's not very far in front of you. It would look to that it was 3 times 10 to the 8th meter per second every second in front of him. So we got this strange thing. Now, the good news about relativity is it leads to some fairly easy experimental sorts of things. Let's talk first about how you can turn this into numbers. What? You can turn this into numbers? Yeah, we can turn this into numbers because we're physicists. That's what we would do.